Yes, so we're all familiar with climate issues. And what I'm going to do today is just show you some examples from our museum, the Museum of Cultural History, which will probably be familiar to many of you. And what I'm going to do is show you some snapshots from 2019. First of all, we'll just talk about our buildings. So we have, the Museum of Cultural History has about 1.6 million artifacts, and our collections are mainly housed in 3 buildings, all of which are listed for preservation. The Historic Museum is located in the center of Oslo, and it displays archaeological collections up to 1537 AD, objects from indigenous and world cultures, collections from antiquity. We have a coin collection, medieval church art, and church inventory. At the Viking Ship Museum, we have, which is located on the Big Day Peninsula outside of the center of Oslo, we have Viking ship burials displayed there. And finally, in the main stores and laboratories are located in a separate building, just a few metro stops from the center of Oslo. So if I start with our main storage and laboratory building, so it's our most modern building. So it was built in 1957, and we've been using it since about 2006. In the early 2000s, we received state funding to upgrade storage areas. And in connection with these upgrades, this building was rented. And we have been slowly moving into it for the past 10 to 15 years. This building has been completely refurbished inside, but we are still working on it. It's quite a complex building where we have a lot of independent HVAC systems. And our main aim here is 50% RH and 18 degrees Celsius year round for climate, for most storage. We have a we have some special storage though for cooler cool stores. So either from 8 to 13 and we also have dry stores, so less than 15% humidity. We have a fire suppression system using inert air, which means using lower oxygen levels than normally found in air, which will suppress any flames. We have strict IPM routines. And here I'm going to be introducing a little bit of the ASHRAE storage and museum space classes. ASHRAE is the American Society of Heating, Refrigerating, and Air Conditioning Engineers. I'm going to be trying to relate these to our rooms. So ASHRAE is, since 2007, the handbook published by ASHRAE has included a chapter on museums. And here they classify museum spaces according to how tightly the climate, that is the relative humidity and temperature, are controlled. And here I've made an excerpt of that table. The starting point here is 50% RH and 15 to 25 degrees Celsius. And I've used this table to categorize our storage and lab spaces for this presentation. And generally, the table goes from very strict control, so you have AA classes, down to D, which I don't show, but I show only up to C. And generally, the stricter the control, the higher the letter, closer to A. And as we release control over the climate, we increase the risk of damage to our objects. So this is how they've defined it. I won't go into the details of the table, but here you can see there's general short-term fluctuations and seasonal adjustments, which have been worked into this table. So if we just move on to Ökern, so the general collections, how does it look? Here we have main aims for rooms are 50% humidity and 18 degrees. And the archaeological material and polychrome wood sculpture storage room has quite good control, as you can see on the graph here. I guess we would call this an A or double A or A, according to ASHRAE. And here that you can see that the humidity is quite stable. We do have these hiccups, which I don't quite understand. It's probably something to do with maintenance, but I don't really know what that is. And here we have, examples of some objects in the storage area. In our indigenous world cultures storage, we have, this is an example of an object in there, Kachina doll. Here we have also the same aim, it's 50% RH and 18 Celsius. Here we see a little bit more fuzzy RH from the, like deviating a little bit from 50, and especially something is going on here in the fall of last year. And I'm not sure if this is something that is normal or if something that was just a special issue that happened then. I'd have to go back into the history of the climate to see that. And here we also at Erkern, we have the special stores. So here's an example of the archaeological metal storage that we have, that we are currently working on. There are no objects in here yet. And here we have the aim is below 15% RH due to the sensitivity of archaeological iron objects. And then here we have an example of the cool stores for skins, fur, feather basketry, which looks amazing. It's set to be at about 13 degrees Celsius, and the aim is at 50% RH. Here we have a few hiccups, but it seems to be quite flat. And we chose this lower temperature with the hope of reducing the rate of degradation. In our large object storage, we have a little bit more variation, but it's still quite good. Class A, B, or C. I'm not sure how to really organize, think about the classifications using ASHRAE. But we see that there is some kind of hiccup here in July of last year. And this is probably something that has been worked on since. I'd have to look at the other climate data to see that. Now we have the laboratories at our main building. They're not really as well controlled as the stores. Have we seen damage? I'm not sure. And how is it we can evaluate damage? That's also hard to know. So summarizing this building, our stores and labs, we have a very high-tech building with good conditions for collections most of the time. We're still developing new stores, so this is a very long-term project. It's costly and requires a lot of follow-up, but we gain the peace of mind because of low risk of damage in the long term. Is this the way to go if you have the funds? However, we've seen several deviations from our climate aims during the year of like 2019. And what we have to watch out for are how the disruption affects the risk of damage to collections if this is a regular event, which I would think it is, and how do more uncontrolled conditions in the labs affect the risk of damage when we take things out of storage. If I now move on to the Historical Museum, our next building, as mentioned earlier, this building is mainly used to display our collections. And here the slide shows pictures that show the different kinds of displays that we have there currently. It's also a listed building, which affects how we the type of renovation we can do onto it. It's from 1904. So what I'm going to do is show you examples of climate for 3 rooms, 2 at the front of the museum and 1 at the back. The front of the museum faces northwest, so it gets a lot of sun. And I'm just mentioning that we're in the process of working on the climate in this building as well. So here we have some floor plans from the Historical Museum. And you see in the pink medieval box, this is one of the rooms we're going to look into today. And this is showing medieval church art inventory, building inventory from the Middle Ages. On the second floor, we have two exhibition spaces, Arctic and Egypt. So let's start with the medieval room. So here we have our, it's an open space. We deliberately do not have display cases for the more sensitive painted objects, but we also have a mixture of materials here from metals and ceramics to bone and horn. And the cases that you see here in the picture, they are not tight. Here we have a strict climate wish. So we would like 50 plus or minus 5% RH due to the sensitivity of the painted wood. But currently there's only humidification and there's no dehumidification. So in the summer, as this box here shows, it falls out of the climate range that we want to try and maintain. So as I said, we're working on these issues, and we'll hear more about those later today. If we move now to the second floor, here we have Egypt, an exhibition on Egypt. And here we have local humidification again, and no dehumidification. But here we have climatized display cases. And here we can see that the climate aims for this room lie between 40 and 60% RH, with fluctuations between of plus or minus 5 in 24 hours. And here we see that the room, which is the dark blue curve, is much more widely spread. The RH is much more widely spread than the RH in the display cases. And so it seems like they're definitely buffering the changes in the space. Here we use passive climatization using pro-absorbed cassettes. And the only question I have here is I hope that it's the display cases that are buffering the fluctuations and not the objects. But this looks pretty good. Now, if we go into another display area, Arctic, we have, which is on the back of the building. It's an older display area. And here the display cases are not climatized. And again, there's local humidification, but no dehumidification. And the display case is definitely, as you can see here, we have the background room RH throughout the year. And then the dark black line is showing the climate inside the display case. And it seems to be buffering quite well, but then I just really wonder, is this really buffered by the case, or are the objects buffering it? So this will be interesting to look at when we start upgrading these areas. So just to sum up this historic museum, this building here in the center, we're working on the climate situation, and you're going to hear a little bit more about this from Ida Bryn later on this afternoon. Finally, we have our Viking ship museum. It's currently displaying Viking ship burial finds. The building was built in 3 stages. In 1926, here, in 1932, and in 1957. And today it too is a listed building, and it does not have an active ventilation system. If we just compare the inside and outside weather of Oslo, we can see that well, first of all, I'll tell you how the building is, what it's made from. It's mainly made of concrete and brick. The walls are relatively thick. And inside and outside, the surfaces are painted. So there's not a lot of buffering effect here. But when we compare the outdoor climate, which is in the light gray, to the indoor climate, we see that the building envelope is actually buffering quite a bit. But the lag time, it doesn't really, it dampens the fluctuations from the outside. It also, the increase in temperature here in the winter makes it quite dry because it's slightly heated in the winter. And we've seen that the lag time between the changes outside and inside is very short. So it doesn't seem to affect that. Yeah, inside, these are the inside RHMT. So if we go to the display, here's a view from the different displays. And as I said, we have Viking ship burials here. There's a lot of archaeological wood on display. The smaller objects are displayed in climatized display cases. And the 3 ships and some other larger wooden objects are on open display. So let's compare the climate differences. So here we see the light gray curve here is the climate in the room, the RH in the room. And you can see that it varies quite a bit throughout the year. However, our display cases, which are climatized with Prosorb cassettes, manage to really dampen these RH fluctuations and contain the RH spread between about 45 to under 60, which is not bad. We can, in the main room here, we see that ships are displayed way back here, and this climate is, we're questioning how this affects the actual state of preservation of the ships. And you'll hear later on from David Hauer about what these effects can do to the global deformation on the ship. He'll tell you more about this at 3:30. So just to round off, there are plans for this museum as well. A new Viking Age museum is planned, and it'll be connected to the existing museum, as you see in the circle here. So we're currently working on large climate projects in all of our 3 buildings. It's a lot of work to follow up such projects, not to mention following up the everyday situation in each building and to try and keep up with current research on climate. But our museum is not the only one with new plans, huge new plans. There's a lot of building going on in Oslo right now, and we hope that today's seminar will give insight into climate issues from several museums. Later in the day, we will also hear about research on measuring changes in objects and materials. And finally, we'll get an update on current thinking on climate and practical measurement. So I'm really looking forward to hearing today's talks, and I really wish you a good seminar. Finally, I'd just like to thank my colleagues at the museum for their help in getting information about all the different types of climate situations at the Historical Museum and at our laboratory building. Thank you very much.
Hei, så jeg skal snakke om klimastrategier i nytt vikingtidsmuseum som nå under planlegging. Og for å fortelle litt hvor vi i prosessen nå, vi ferdigstilt kvalitetssikringen av forprosjektet som ble avsluttet i 2017. Så vi har hatt det opp igjen, og nå vi rett på oppstart av detaljprosjekteringen nå i 2021. Så vi se. Her har vi bildet av det nye vikingtidsmuseet som da skal bli bygget på bygde, og det en forlengelse av dagens vikingskipshus. Det bygd av det tegnet av Art Architects, et dansk arkitektfirma. Og det betyr altså det som i dag huser Oseberg, Gokstad og Tune-samlingen. Det som i dag heter Vikingskipshuset skal bli inngangsparti med påfølgende med butikk og auditorium, men da med inngangsparti til det nye museet, der alle da gjenstandene skal flyttes til. I tillegg til dagens utstilling, eller gjenstander som stilles ut i Vikingskipshuset i dag, så kommer det jo også flere gjenstander som vi har hatt utstilt og ikke utstilt i sentrum. Så alle gjenstandene skal stilles ut i det nye bygget. Og da, når vi da skal ta i bruk et nytt bygg, hva slags klima skal vi da sette som, eller klimastrategi skal vi da ha? For vi går jo fra et eldre bygg, som dagens vikingskipshus, ble jo bygget i flere etapper, som Susan sa, så de startet i 1917, og hele bygget, sånn som vi ser det i dag, stod ferdig i 1956. Og her det jo ingen kontroll på klima utover bygningsskallet i seg selv. Ja, så vikingskipshuset naturlig ventilert, og skal vi se. Beklager. Små gjenstander har vi fått utstilt i montre som Susan forklarte, med passiv klimaregulerte montre som reguleres med prosorb, der vi har en klimasperre eller grense på mellom 40% og 60%, og det holder seg relativt greit. Og de fungerer godt, altså. Ja, og her har vi jo både metaller og tre i samme type montre, og det fordi at metallene til fra Osebergfunnet fra disse skipsgravene har vært veldig, veldig stabile, og de tåler dette klimaet. Men så det de store gjenstandene som utstilt da åpent, og da det Oseberg, Gokstad, Tuneskipet og gravkammeret samt 2 småbåter fra Gokstadskipet som utstilt åpent i disse utstillingssalene, som kun blir oppvarmet med radiatorer om vinteren. Og det har relativt liten effekt, heldigvis da, kan vi si, for det fører jo til at det ikke blir for tørt heller i utstillingssalen. Men den følger sesongmessige svingninger i uteklima. Og det jo dette her vi må ha tatt utgangspunkt i når vi også har begynt å se på hva slags klima skal vi sette som krav i det nye bygget, for vi må ta med i mente at disse skipene, dette jo det klimaet de mer eller mindre har vært utsatt for siden 1926 for Osebergskipet, da det kom på plass, og Tune og Gokstad på 30-tallet. Så det vi da har gjort for å da tilpasse oss også vi ønsker et bedre klima i det nye museet, men hva skal vi ta, som blir bedre kontrollert, men hva skal vi ta utgangspunkt i? Og det vi da har gjort vi skal bare først vise hvordan det har vært siden 2017 til 2019, for nå gikk jeg litt fort frem her. Som viser at klima, unnskyld. Klima varierer jo sterkt, som jeg har sagt, i sesongene fra nede i 35% på vinteren og oppover mot 80% på sommeren. Og ved å ta utgangspunkt i senstandarden, så for å se hva som for å finne det spektret der, for å prøve å unngå at skader oppstår, så har vi gjort denne analysen for å se hvor ekstreme variasjonen, og det jo mye eller sånne utenfor for akseptabelt nivå på sommeren, men også en god del vinterstid. Og dette jo fra de 3 siste årene, 2017 til 2019, og da har det vært relativt milde vintre, og 18 var jo også en spesielt ganske tørr sommer. Hva vil da altså med et nytt Braovac-system, hvilke grenseverdier skal vi sette? Vi ønsker et optimalt inneklima for samlingen uavhengig av årstider og antall besøker, men samtidig også ha et lavt energiforbruk. Det er tankene bak de nye museene. Så det slik vi fortsetter å tenke på klimaregulering av monter i nytt vikingtidsmuseum, så det fremdeles passivt klimatisering som der vi vil ha montere som sikrer en 0,1 luftskifte per døgn. Og vi vil bruke silikagel for metaller for å holde en lavest mulig RF og prosorb for mer organisk materiale. Og så ser vi også at det er viktig at vi må differensiere klimaspektret for de alunkonserverte gjenstandene. Da også der alunkonserverte sammensatt av mer kompositter, altså sånn av annet nytt tre for eksempel, som kanskje vil reagere annerledes til høyere luftfuktighet enn det alunkonserverte så det vil vi jobbe mer med. Så var klimakrav for gjenstand utstilt åpent i det nye vikingtidsmuseet. Og det her vi også har tatt utgangspunkt i forprosjektet, tok utgangspunktet i hvordan i de klimamålinger som ble gjort før 2017. Og da har vi tatt utgangspunkt i en analyse som ble gjort av klimamålinger gjort fra 2009 til 2012. Som dere ser, så her målingene ganske tørre enn det var i de målingene jeg viste fra 2017 til 2019. Der det glidende gjennomsnittet som den blå streken ligger på mellom 30 og 70%, men den tidligere grafen jeg viste for de tre siste forhenværende årene, da var det mellom 40 og 70. Så det gjorde at vi har lagt listen, at vi aksepterer et noe større spenn, og har lagt en årlig, det som vi da kom med anbefaling til relativ luftfuktighet og temperatur i det nye vikingtidsmuseet, var mellom 35 til 65% relativ luftfuktighet med maks 5% svingninger per døgn og temperatur på mellom 16 og 25 grader. Og vi ønsker å operere med 2 settpunkter for vinter- og vårhalvåret og for sommer- og høsthalvåret, der vi også tillater 10% svingning per sesong. I særutstillingen derimot så har vi i utgangspunktet lagt et litt smalere spekter med tanke på innlån, og slik at vi vil ha en årlig svingning på mellom 45 til 55% RF, og settpunkt på 50% med en variasjon på pluss minus 5% per år. Så hvordan ser dette da ut i dagens, eller i de grafene vi har, eller de målingene vi har gjort, og det klimaet vi har nå i Vikingskipshuset, så vil vi jo prøve å jevne ut grafen, fjerne topper og bunner, og få en jevnere, slakere graf da, og et bedre oppbevaringsforhold for gjenstandene. Og går vi til neste grafen som ble gjort for de siste 3 årene, så ser vi at vi er mer nærmere der nå også. Men dette i hovedsak anbefalte spenn for den klimatiseringen vi ser for oss i nytt vikingtidsmuseum. Altså vi aksepterer svingninger, men det skal være langsomt over tid, Og det viktig at vi også ser på grenseverdiene I forhold til det systemet som vi faktisk nå går I detaljfasen med å planlegge. Og det må også ses I relasjon til bygningsmassens bufferkapasitet, og hvordan det vil ha en stabiliserende effekt på temperatur og luftfuktighet. Og sist, men ikke minst, så det også få den kunnskapen vi nå, som David nå jobber med, å få om hva skipene faktisk tåler. De foreløpige anbefalingene må verifiseres opp mot hva skipenes globale deformasjon og hvordan de faktisk beveger seg til denne, altså sånn til dette, I dette klimaspennet. Så det vel egentlig der vi står I dag. Nå vi detaljeringsplanene på gang, og ja.
Thank you for being invited to present this work. This is a little study that was made during the lockdown in the spring. The background is a historic museum in Oslo. This is a building that was finished in 1902. And at that time, this was a most modern building in Oslo. The building was designed to host a historic museum. This can you see, it is reflected in the design, and it has all the time been a historic museum. The museum houses objects of different kind. It's wood, textile, metal, painted objects, and all these have different requirements to climate. Originally, it was planned with natural ventilation with the exhaust through towers. You can see the towers on the picture on each side of the entrance. And it's, I think it's 6 or 8 such towers around the building, which are connected throughout the whole building through ducts and integrated some kind of integrated ducts. And the building also, it had single pane windows, what was common at that time. But later mechanical ventilation was installed, and later again they got humidification in the ventilation system. This ventilation is not connected to all areas. Some areas still have the natural system. And so these areas have also local humidification. The building is protected, also the windows and the facade. So to provide better insulation, double pane windows was installed on the inside, as you see on the picture to the right. And the windows, they can also be opened. It's been seen the last winter that they get condensation between the windows in 2nd and 3rd floor, and that happens when outdoor temperature is below a certain degree. And of course, this condensation depends on the indoor humidity. So the question is, why do we have this condensation, and why don't it condensate in 1st floor? It has only been seen in the 2nd and 3rd floor. So we have made some study to try to understand and describe this situation, because initially the people working with the renovation, they thought that this was a wrong delivery, or it was a not satisfactory delivery with these windows, that they were not tight enough. And all these new windows, they are possible to open as shown here, and they might be tight, but they are not sealed, and it's not possible to get them 100% airtight. And overpressure in the room related to the ambience, that will press air from the inside to the outside. And because of this, we understand when we have condensation in the second and third floor, that means that we in some periods have overpressure in these areas. So why don't it condensate in first floor? We have to look at the pressure in the building, and the pressure it is caused by forces. It's wind, and it's buoyancy, and it's a mechanical ventilation. And it all work together. So only from this you can understand that this is quite volatile situation because of the nature that has such a big influence. And that is a force situation. And if you look at the other situation that influences is the building structures. So that is the opening types, the doors, the cracks, and the natural ventilation system, of course, that is still there and has the influence. And especially it's the opening areas and the height between the height difference between openings that have a big influence on this pressure and airflows. I'm not going to take you all the way through the physics in this, but you have in a balanced situation with the same size of the openings in the lower and the top of a space as you see on the right, then you will have and no wind and no ventilation. If it's only the temperature that is a force that make the force, the buoyancy, then you will have a neutral plane in the middle of the building as shown on the figure. But if this area is, for example, all the openings are in the low part of the building, then if you study this these equations, you will be able to detect that you will have overpressure in the whole building. And in the opposite, if you have a big opening in the top, it would be like a pipe, and you get not a pipe like a chimney, and you will get under pressure in the whole building. And these natural ventilation systems, they are made like chimneys because they want to make the air go through the building. So that was the base that we wanted to make some measurements. And we wanted to measure the pressure difference between inside and outside, the temperature in the room, and the humidity in the room. And we measured in the Middle Age, the lobby, second floor Arctic, third floor Viking, and third floor UPS office. And here you can see a picture on the top. I have put in the temperature situation that day, the outdoor temperature. That was a Thursday, 26th of March. And it was a situation when we had expected to have normal ventilation. And below the temperature, you can see the wind. It's very little wind that day. And in the bottom, you can see the overpressure in or not the overpressure, the pressure difference between these rooms and the outside. So if we, for example, look at the first floor, Middle Age, that's a Turkish one. So then we see a quite stable situation, and then it drops the pressure from 6 to 3 o'clock, and then it's stable again. And so we see that there's a fluctuation, the change in the pressure situation between 6 o'clock and 3 o'clock, and that is caused by the ventilation system that makes a change in a pressure in the building. So if we go to the next slide here, we can see still it's the same picture of the pressure to the left, and to the right you have the upper right to the right, upper Yes, the upper picture there, you can see this is a temperature, and down here you can see the humidity, and I guess that's what you are very interested in. And what you see here is that this is UPS third floor UPS office, and in second floor Arctic, we see there's a low humidity, not low, but it's lower, and it increases during the day, and then it falls again. And this is the ventilation system. And these three others, they have very little influence. It's stable all day. And that means that I guess they don't have any ventilation by this from the mechanical ventilation. They are, the middle age is humidified by its own humidifications. And the same to a certain extent in the other areas, I guess, because I would expect maybe a lower like this, or even lower if there is no, yes, the vestibule, I guess there is no humidification, so this is without any. And as you see, the pressure varies from quite high under pressure in the foyer, and here in the third floor Viking, we have overpressure in periods. And also here, and you'll see other slides later on that you can see we have overpressure in also the second floor. So because this under pressure here in this foyer, it makes draft, for example, when you open doors. So this was with the closed doors to the exhibitions, and here we had a day where we had open doors to the exhibitions, still ventilation, and then you see a much more stable situation on the pressure, but we see the same pattern with humidity. It's stable during the night, and then it increases when the ventilation is switched on. And here, for example, in this office, it's quite low during the night, and it increases high. Here we have a day with no mechanical ventilation, and this is a day that is quite windy. You see down here, this is the middle wind, and this is the maximum. So it's I don't know the English terms for wind, but it's cooling. I think almost cooling in Norwegian. And we see it has big fluctuations on the pressure here. And we have overpressure, as you see here, also in the Arctic. And to the right, you see this is temperature. It's relatively stable. But here you see the humidity is quite stable, but then with the wind, it falls. So it has a big inflation on the whole building. This maybe the middle age is the best that keeps the humidity, but the others, they fall quite low. And that is infiltration in the building, auto air that causes. And here is another day, and there is also a day without ventilation, because you see the humidity is stable, but here it increases, and that's here it's little wind, so it's little infiltration, and then you don't lose the humidity. So what we see that when the ventilation is off, you can go back. You see here's the ventilation off. Most of the building is and has under pressure. It's only the third floor that has overpressure. That means that the old ventilation towers still work as a chimney for the building, and but then when the ventilation is on, it influences the pressure, and then you also get the overpressure in some areas in the second floor. And we see that the humidity in the rooms increases when the ventilation is on, but it falls quickly when it's off. But we see that in the third floor Viking, it's mostly under pressure when the ventilation is on and the humidity decreases. So there we wonder if there is a lack, maybe there is no ventilation supply there, and so that only ambient air arrives, because it's strange that it's under pressure there. And we see that the climate in the building is relatively volatile. And I think that the only way to get full control of the temperature of the objects is to keep them closed in closed climatized boxes, because it will be, I think it will be almost possible to get a stable situation in this building. And so the next question, so now I've explained the pressure difference and why we get different pressure. And then the second is why do we have condensation? And as you see from a Sunday here, the 29th of March, we have overpressure in both the second and third floor. It's around between 1 and 2 Pascal, so it's very, very little. But if you look at the windows, they are according to the standard. If we consider that they are according to this standard, NS 12207, then we can calculate how much air that is pressed through the window with 2 Pascal overpressure. And if you assume a window with a 2.3 by 2.3 meter and that they have 3 openable parts, then we calculate, the calculation shows that up to 1.17 cubic meter per hour passes through the window. And what happens then? You have this 1 something cubic meters that goes through this double pane inside here and then out here. In this room, if you have 20 degrees and 50% relative humidity, you have a dew point temperature, 9.3. That means that you get condensation at 9.3 degrees. So the air is pressed out here, and the temperature here, when it's -3, this is just a calculation, when it's -3 outside, then we have 1 degrees here. So this means that you get condensation because of the heat loss, because there's a lot of insulation in this window. You get a drop in the temperature here, and you get condensation here and on the surface. So you might get, for example, between 2 to 4 grams per hour when the temperature outdoor is -3 degrees. So we see that air is pressed out through the windows even at low overpressure. And as long as there is overpressure in the building, condensation will occur when the temperature outside falls below 6 to 7 degrees. And more the colder. And this condensation will also occur in other parts of the building, for example, the envelope, part of the building envelope as a roof. So we have looked at a possible step-by-step solution to see if we can do something about it. I think the best for the building would be to always have underpressure in all areas with humidification. And we should have a continuous online registration of pressure, humidity, and temperature in the whole building. We could start with a manual control of the ventilation to get the underpressure when we have installed the measurements, and then test. And if it works, you might convert to automatic, that runs the ventilation to achieve this. And I also think we should turn off humidification in the ventilation system, and maybe see if it's possible to reduce the mechanical ventilation to minimum when ambient temperature fall below 6 degrees. You might need relatively high ventilation in the summer period because of the cooling. It becomes too warm if it's, because it's big windows. And we should preferably use local humidification, and the most important, prefer humidification inside closed climate boxes. Yes, and that was my conclusion of this study. It was a very little study, and it's hopefully we can get better situation in the museum by doing this.
I will start with a little bit of history. For those of you who don't know this, the rest of you have to bear with me. The National Museum was founded in 2003 as a fusion of several big national institutions. The National Gallery, the Museum of Contemporary Art, the Museum of Decorative Arts and Design, the Museum of Architecture, and later on also the National Touring Exhibitions and the Stenersen Villa, which is a separate building. So until now, all of these, even though we were fused in 2003, we didn't get the new building until now, and we still haven't quite been able to move in. This is the new building, this structure here. And these are buildings that were there, but that are protected by they are part of cultural heritage. So they, the architect had to sort of, make a balancing act to get this building a bit behind the existing structures. So the National Museum has a gross floor space, as you can see, 54,600 square meters. And I wanted to go back now, actually. No, this is way too fast. And we have an exhibition space of 13,000 square meters. This, the main feature of the building, which is the light hall, I don't think you can see my, can you see my pointer? No, you can't see that, I think. But it's this, the top structure in the middle of the picture, that's the light hall. And that in itself covers 2,400 square meters. That's for temporary exhibitions. We will have a storage space of 8,000 square meters also within the building, which was a really a thing that was discussed a lot, obviously, because the price in the center of Oslo is very high per square meter. And it was not a given that we would have our storage space also within the building, but that we succeeded in getting most of the storage there, which is really great. Just a comparison with the exhibition space that we had before in the separate buildings, not the architectural building, which we will still keep as a separate building, but in the buildings in the museum buildings that are now will be moved out of. The National Gallery, we had 2,000 square meters. The Museum of Decorative Arts and Design, we had 2,200 square meters. And the Museum of Contemporary Art, about 4,000 square meters. So in all, we will, in the new museum, get, as you can see, a lot more exhibition space, not just for the presentation of the collection, but also for contemporary exhibitions. And I brought this slide as well because I was myself surprised to see that we are actually have more exhibition space in the National Museum than other famous and very large museums. So it's a really, really large structure. The National Museum has about 400,000 objects, ranging within, ranging from all kinds of different materials. And I will just show you some of the objects that we are going to exhibit and to store, also because they're very nice to look at, but you can see that the span in objects is from medieval textile through costume, precious glassware, very light sensitive mixed media on paper, mixed media on cardboard, iconic objects like this one, silver and enamel objects, architectural drawings. Most of those will be kept, I have to say, in the Architectural Museum, but some of them are going in on exhibitions in the new National Museum as well. Architectural models, the same. This is a model for one of the early models for the opera building, if you may recognize it. And a lot of posters, paintings, installations, in this case, reindeer skulls, sculpture in all kinds of different materials, and precious Japanese lacquerware. So you see the range of materials and their requirements is quite big, and they also come from quite different conditions and will be moved into the new building. So the Museum for Decorative Arts, they house absolutely the majority of the objects, lots and lots and lots of different objects. And that building is going to be emptied out. We are in the process of doing that now. And everything moves into storage or exhibition space in the new museum. The Museum for Decorative Arts is a building without any climate control at all, just like the National Gallery, which you see here. And the National Gallery houses sculpture, paintings, and works of art on paper. And the conditions, the climate conditions here, I was actually a bit surprised that our neighbor on the other side of the square, the Historical Museum, which we just heard an interesting talk of, that you don't have higher temperature in summer, because in the National Gallery, the summer temperature may reach 30 degrees. And in winter, it's the dryness that is the biggest problem. The Museum for Decorative Arts have exactly the same type of range of temperature and humidity, or lack thereof, in winter time. Whereas the Architectural Museum has climate control, has climate controlled areas. We also moved from 2 external storages, which are climate controlled. So as you can see, the move itself creates a bit of a problem, because we would have preferred to have moved all the climate sensitive things during summertime, when the differences between the new space and the old space would be the least. It's not, we don't know at the present moment when we will be able to move, but we hope that we can arrange it so that we can move the more climate sensitive objects during this late spring summer season. In 2009, we were asked to present our requirements for indoor climate in connection with the room program and the functional analysis that were supposed to be the basic documents for the architectural competition. This was won in 2010 by the current project, by the architects Klima and Storevik. The requirements at that point was presented by my predecessor and later boss, François Sansen-Bauer, and she, in collaboration with the conservators, had done a fairly thorough job in getting acquainted with the current international research on indoor climate. So by 2009, there were already new proposals for new and less strict standards on their way. And it was also a pronounced wish from the contractor, Statsbygg, that the building should have as a small carbon footprint as possible and be a passive building that would in itself slow climate changes down. So we ended up with this as climate requirements for the exhibition halls. You can see we have specified we are within the range of 40 to 60% relative humidity and 20 to 24 degrees in temperature. And with the 24-hour variation of ±2% when it comes to the temperature and ±5% when it comes to relative humidity. So you can see here we have specifications throughout the year that we have presented as part as the requirements. So we want to we would like to have between 45, we have 45% as a set point during winter time and 55 during the summertime as a maximum and minimum set point. And the temperature around between 21 and 24 degrees. Or 20 and 24 degrees, as you can see. When it comes to the storage, we want to have a cooler temperature all over in the storage. We started out with quite specific requirements for all types of materials, and it was pretty soon clear that we would not be able, we had to group them together in a more pragmatic way. We couldn't have very specific requirements for all the different material groups. So we ended up with larger groups, a larger group requiring cooler temperature and a larger group requiring a temperature from 14 to 20 degrees. We have 40 to 60% relative humidity with slow seasonal changes for everything except for certain materials like fur, leather, and photography, negatives, slides, and so on. Metals would also require ideally a drier climate, and it's possible that we have to do something locally there. As you can see here, we have not required that specifically. We have said 40 to 50, so it's slightly below the 40 to 60 range. We are not, there are problems. There are absolutely problems here. There are problems that we haven't solved. We wanted ideally to have a cool room for all the stuff that needed cooler temperatures, and we haven't got that. So we have to solve that locally with not refrigerators, but with cool cupboards and maybe some kind of climate cupboards for the objects that need a drier climate. So we need to work locally, and we are at the present moment not quite sure how we will do that. Whether it's possible to do it in the existing storage rooms or whether we have to dedicate storage rooms in the basement to do this properly without producing too much heat that cool cupboards will absolutely produce. So this is a big question mark at the moment, but something that we have to address and we have to solve. So this is a picture to symbolize that the museum is not yet quite ready. We don't know exactly how the climate will be, but the readings we have got so far they seem to be very convincing, I have to say. The building is supposed to be a passive building, and the indoor climate should react correspondingly, react slowly to outdoor changes, and that seems to be the case. We have now readings from, I think we have consistent readings from about a month. Prior to that, we had point readings from certain rooms in the museum, but not all of them. But we have now an overall readings the past month, and it seems to be, it seems quite good actually. But there are, as I said, there are still unsolved issues, and we don't know what this will look like when we have people in the house, visitors. We don't know that. We have a lot of showcases, and we will, and some of them will be locally climatized. So we will have for certain, for metals, for instance, and for other very sensitive, humidity sensitive objects, we have the possibility to make microclimate in the showcases. So I want to come back to you in about 2 years' time, and then I can tell you how it worked out. So far, this is where we are now, and I would love to be able to tell you in 2 years that everything worked according to plan. Thank you very much.
Det har vært normen i mange museer frem til de siste årene. Den relative luftfuktigheten ligger på 45–55%, og temperaturen på rundt 20 grader. Temperaturen i papir- og malerimagasin litt lavere. Det var særlig 3 utfordringer ved de gjeldende restriktive klimaverdiene som vi tok stilling til. Den første at det mangler tilstrekkelig med forskning til å bevise at dette var nødvendige verdier. De energikrevende og kostbare, og ulike materialer og sammensetninger krever ulikt klima. Et hovedspørsmål museer og samlinger står overfor hvorvidt gjeldende klimaverdier kan endres. Allerede i 2014 kom ICOM-CC med retningslinjer for klima i internasjonale låneavtaler. Retningslinjene anbefaler klimaverdier som bredere enn de Munchmuseet har operert med frem til i dag. ICOM-CC oppfordrer museer og samlinger til å redusere energiforbruket og klimagassutslipp. En av hovedutfordringene i bygget på Tøyen har vært bygningens konstruksjon. Gjentagende vannlekkasjer og kondensproblemer på utstillingsveggene i perioder med vått eller kaldt vær. 2 av veggene i utstillingssalene i dag yttervegger. Vi har også hatt vansker med klimaanlegget, også særlig på 90-tallet og litt utover på 2000-tallet, inntil systemet ble oppgradert for omtrent 10 år siden. Etter det har klimaet vært stabilt, men med noen avvik i ny og ned. Det har også tidvis vært en utfordring å holde luftfuktigheten innenfor de gjeldende verdiene i maleriatelierne. Når det sagt, så det viktig å presisere at maleri- og papirmagasinet har stort sett holdt stabile verdier over flere tiår. Så vil jeg si at selv om vi har et felles ansvar for verdens klimasituasjon, må bevaringsansvaret for kulturhistorisk materiale og kunst veie tungt. Det viktig å legge til at energisparing også kan gjøres på andre områder enn ved å endre temperatur og luftfuktighet i områder med kunst. Det nye Munchmuseet har en indre betongskjerne med mange klimazoner styrt av et klimaanlegg og en ytre del med passivt klima. Kunsten skal stilles ut og lagres i den indre kjernen. Bystyret i Oslo kommune ønsket at hele det nye bygget skulle tilfredsstille passivhusstandarder, og at miljøegenskapene skulle vektlegges ved materialvalg. Alle ventilasjonsanlegg har stor grad av varmegjenvinning for å utnytte den tilførte varmen best mulig. Men kravene til temperatur og RF for området med kunst innebar at passiv klimastyring ikke ville være mulig å gjennomføre. Altså ble anbefalingene fra ICOM-CC om passiv klimastyring kun mulig å gjennomføre i den ytre delen av det nye museet. Bildet viser byggingen av den indre betongkjernen i det nye Munchmuseet i Bjørvika, før den ytre delen og skallet bygget på. Betongkjernen ligger innenfor den passive klimazonen i vest, synlig på tverrsnittet til høyre på tegningen. Hvert rom i den indre kjernen har flere temperatur- og luftfuktighetssensorer samt CO2-målere. Det var flere holdepunkter vi la til grunn for klimaendringene. Gjeldende gamle verdier, Munchmuseets erfaringer over flere tiår, samlingens materialer og materialenes egenskaper, retningslinjer fra ledende organisasjoner og institusjoner, standarder, forskningsresultater på materialenes egenskaper, bærekraft og energisparing, det nye klimaanleggets muligheter, utlån og innlånsavtaler, publikumskomfort, og publikumsvolum. Med publikumsvolum så det jo sånn at mennesker og elektroniske apparater, belysning avgir varme og fukt som kan påvirke temperatur og luftfuktighet i et rom. Risikoen øker med antall mennesker og aktiviteter. Det nye klimaanleggets kapasitet ble ikke vurdert inn som et holdepunkt når vi skulle revurdere klimaverdiene, men det var likevel en faktor som vi så på. Så for de av oss som ikke konservatorer, så tenkte jeg at jeg skulle bare kort gå gjennom historien som viser opphavet til det man kanskje kan kalle i dag en slags norm for hvilke klimaverdier vi har i museene i dag. Og hvorfor denne normen har blitt anvendt av så mange samlinger og museer over så lang tid. Denne historien kan kanskje gi en forklaring på hvorfor den har blitt stående så lenge med så relativt restriktive klimaverdier. I 1924 installerte Cleveland Museum of Art et klimaanlegg som skulle holde RF på 50–55%. I 1920 etablerte faktisk British Museum sin første vitenskapelige laboratorium, da de oppdaget store skader på objektene i samlingen etter oppbevaringen i tunnelene under London under første verdenskrig. I 1940 kom publikasjonen The Manual on the Conservation of Painting. Den anbefalte en pragmatisk tilnærming til klima i museer og samlinger. Argumentasjonen for å holde RF på 60–65% hviler hovedsakelig på anleggenes mulighet til å greie å holde stabilt klima innendørs. I tempererte klima anses luftfuktigheten rundt 60% som enklest å holde. Det vektlegges også menneskelig komfort. Beklager dette med lysbildene her. Også lagringen av kunst- og kulturhistoriske objekter under den andre verdenskrig fikk betydning og konsekvenser for klimaverdiene i tiden fremover. Utover på 50- og 60-tallet kom flere viktige publikasjoner, og i 1978 publikasjonen The Museum Environment. På dette tidspunktet var imidlertid klimaverdiene på rundt 50 RF og 20 grader etablert i museumsverden. Den gangen var energi billig, og man antok at små variasjoner var ideelt for objektene. På 80- og 90-tallet ble det stilt spørsmål med om disse etablerte verdiene, og utover på 2000-tallet kom det mer fleksible retningslinjer basert på forskning over flere tiår. Men det er viktig å merke seg at det også eksisterer andre oppfatninger. Blant annet forfekter Dørner-instituttet en mer restriktiv holdning, og det eksisterer også en mer pragmatisk tilnærming med fellestrekk til den vi så i de første klimaveilederne, hvor man vektlegger viktigheten av å unngå ekstremt klima og store fluktureringer. Oppsummert kan vi vel kanskje si at flere holdninger opp gjennom historien har vært gjeldende, både påvirket av faktorer som erfaring, klimaanleggenes kapasitet og hensynet til kunst og publikum. Det er først i de senere årene at energiforbruket og klimagasser er kommet inn som en faktor som vi må ta inn i vurderingen av klimaverdiene våre. Så går jeg litt tilbake til fakta. Nedbrytning av kunstmateriale kan skje på 3 måter. Biologisk. Mugg har optimale vilkår i mørkt stillestående luft ved 70% RF og høyere, og samtidig temperatur på 21 grader over noen dager. Så det er kjemisk. Vanlig romtemperatur er ofte for varmt for flere organiske materialer, papir, lær, film og fargestoffer. Mekanisk. Generelt sett utgjør store sesongvariasjoner større risiko enn flyktige små fluktureringer. Og det skyldes at de fleste materialer bruker tid på å oppnå likevekt med klima i rommet. Så vil jeg bare presentere fort noen tidligere forskere på klima og bevaring, som i ganske stor grad har medvirket til de klimaendringene som vi ser i dag i flere museer. Smithsonian Institute er verdens største museum, utdannelse og forskningskompleks. De opererer nå med verdier på RF 45%, pluss minus 8%, og temperaturer på 21 grader, pluss minus 4 grader, i magasin og utstilling. Men de har unntak for skjøre materialer og flere materialgrupper. Michaeł, som jeg allerede har nevnt, påpeker at RF må holdes under 60%. Det er for å unngå mugg, og fluktureringer mener han ikke bør overstige pluss minus 10 prosentpoeng. Det er for å unngå mekaniske skader. Responstid under en time er sånn som han har vurdert det, ikke et problem. Til slutt så vil jeg bare nevne instituttet IPI, som lenge har arbeidet med å oppnå optimale klimaverdier for kunst- og kulturhistoriske objekter. Basert på fakta og historie fortalt så langt, så foreslår altså Munchmuseet å endre sine RF- og temperaturverdier. Vi utvider RF til 40-60% i alle rom. Fluktureringene må ikke overstige 8 prosentpoeng på en time. Temperaturen i papirmagasinet opprettholdes på 15 grader og malerimagasinet på 18 grader. På øvrige rom med kunst settes maks temperatur til 22 grader. Metallplater og bronseskulpturer skal oppbevares i tørt klima, helst i RF under 35%. Vi vet at graden av mange kjemiske reaksjoner dobler for hver 10. grads temperaturøkning. I svært ustabile materialer kan 5 graders økning føre til det samme. Vi har derfor valgt å holde temperatur litt under det som enkelte standard anser som forsvarlig. Som jeg nevnte litt tidligere, kan også antall mennesker og aktiviteter påvirke temperaturen i et rom. Vi ønsker derfor å holde oss godt innenfor yttergrensene, slik at vi kan ha full kapasitet på antall besøkende, uten å risikere å havne over forsvarlig temperatur. Med disse generelle klimaendringene følger det noen betingelser, som for eksempel at konservator blir varslet ved brudd, og risikobeskrivelser for enkelte objekter. Forhåpentligvis så følger det også med en del fordeler relatert til anleggets mulighet for energisparing i den daglige driften. I endringene ligger også unntak for flere objekter. Mange av disse er ikke objekter som Munchmuseet har i samlingen sin. Hos oss så gjelder det hovedsakelig hensyn til foto med celluloidfilm, metallplater og bronseskulptur. Disse objektene, metallplatene og bronseskulpturene, får egne kjølrom, og det samme gjelder også fotomateriale som må lagres kaldt. Vi må også ta hensyn til at samlinger og museer vi låner verk fra kan operere med å kreve smalere klimaverdier enn de vi innfører i nytt bygg. Denne problemstillingen må vi prøve å finne løsninger på i hvert enkelt tilfelle. I det videre arbeidet er det viktig å følge opp nye forskningsresultater og hensyn til særskilte verk, og sørge for at det er tett samarbeid mellom konservatorer og klimaanleggets spesialister. For eksempel anbefaler nyere forskning på vår malte skrik at den skal oppbevares og stilles ut i RF under 45% eller lavere på grunn av nedbrytningen av fargelagene med kadmiumgull. De verdiene som er presenterte nå ble vedtatt av Munchmuseets styringsgruppe i januar i år. De nye verdiene vil gjelde for det nye museet. Implementeringen av de nye verdiene i utlånsavtale er under arbeid, og vi må tilpasse i en overgangsfase de ulike avtalene med innlånerne. De neste slidesene er det ikke meningen at dere skal lese. De har jeg egentlig bare tatt med for å vise omfanget av litteratur som vi har prøvd å gå igjennom. Og det finnes masse litteratur om temaet der ute, veldig mye og veldig mye mer enn hva vi har lest. Blant disse er det forskningsresultat på særskilte verk, ulike materialers egenskaper, nedbrytningsprosesser i forskjellige materialer, retningslinjer, anbefalinger, artikler om bærekraftige museer, andre museers erfaringer og noen standarder. Til slutt vil jeg bare presisere at standarder er retningslinjer, forslag til løsninger, og de er frivillige å bruke. Standarder inkluderer ikke alle eventualiteter. For eksempel beskriver enkelte standarder at temperatur på 24 grader er fullt forsvarlig. Det standarden ikke tar med publikumsvolumet eller en bufferzone for hvor mye man maks kan utsette maleriene for av temperatur. Det er grunnen til at vi har valgt å sette øvre grense på temperatur på 22 grader i våre nye klimaverdier. Det var i grunnen det jeg hadde. Og da takker jeg for oppmerksomheten.
Okay. First, I want to say thank you to Susan and Guro for having the first parts of the climate at the museum. I won't cover that very much in my presentation. And also a thank you to Susan for, I'm stealing her front page for my presentation and brutally just wiping her name out and putting my own name in. That's just the front page. But the presentation is about understanding the effects of fluctuation in relative humidity on the objects. So there has been an increasing interest in large structures and how to monitor relevant parameters of these structures across several museums, the Mary Rose, the Bremen Cog in Germany, the Vasa ship in Sweden, and of course also our own Viking ships and our other large objects in exhibition. So one of the basic challenges of large complex objects of archaeological wood, that is that structural change will give a risk of material deterioration. So there are several, the most critical factors of structural change are climate and of course support systems and also vibrations. So today I'll focus on the on our Oseberg ship and what we see of change both at the Oseberg ship and a bit on the Hjulstad ship, and also to try to introduce what special challenges we have with these large wooden structures. They are complex objects as to they are constructed of many fragments and components and put together as one structure, and they will respond in a manner that is not very easy to predict. And as I will speak a bit about later, it is also a very it's very important to think on these objects as global structure on an overall level, because they can behave very differently on a global scale than if you do analysis on smaller parts of a structure. These are a couple of drawings from the Oseberg ship and the Hjulstad ship. They are mainly made out of original oak from these are burial ships, and they've been in soil for about 1,000 years. And the gray zones on these drawings, that is original material. And it adds up to about around 90% of the structure is original material, and the purple areas, they are recent wood that was used during reconstruction. Several of these parts that are replaced with new wood, we have them in store, but they were not structurally sound to use on the reconstruction. So the complex objects, they are, for instance, in the case of the Oseberg ship, they are constructed of many components, fractured components that are put together. Here we see an X-ray from the side of the Oseberg ship. So in addition to the rivets and nails that were used originally to put the ship together, during reconstruction, there was used a massive amount of nails and screws and metal plates to put the ship together. And all these mechanical joints, they will of course be playing a part on the overall behavior of the structure. If we go into the damages we see at the ship, we have, this is the Gokstad ship. And we see these supports along the side of the ship. They are iron tubes that have a small plate on top that is that the ship is resting on the sides, and then the rest of the mass of the ship is resting on the keel. And then we see between the supports, the sideboards, they are coming down slowly. We also see fractures due to local tensions in the structure. We see fracture formations. So even though the left picture here is from 1959, and the identical bolts you see from 1971, and in 1971 we see a crack between the two same bolts. In 1959, this ship had been on exhibition for about 27 years. So it had been, it had avoided a crack just in this area for many years, and then at some stage we get these fractures appearing. And these are this phenomena of cracks we see especially at the stem and the stern of the ship, at the end and back in front of the ship. And here is from the Oseberg ship. We see this ship is from when the king visited the museum in 1957, and the last part of the museum was built. And if we focus, it's very interesting to use these old photographs to look at damage, development of damages. So if we take a closer look at this frame, red frame, we see this area from 1957. We can see this rivet within the red square that is showing that it's perfectly sound with wood around, and the situation today to the right. There we have about 20 millimeters distortion on the upper board on the port side of the Oseberg ship, and it's the nail is just pulled out of its original hold. So how to approach the response to fluctuating climate? At what level in the structure can you do your measurements to response? Then you have the material level, where you can, of course, it's very, that has been done a lot within conservation and conservation science to look at how the material is responding, both with regards to absorption curves, dynamic vapor absorption, also mechanical testing one can do at different levels of RH to see how the material is responding. Then one can also look at the component level. The component is then, for instance, on the ship, one sideboard, one piece of wood. How is the deformation of the component related to climate fluctuations? We've done this on the Oseberg ship. Susan and Paolo, a wood scientist, and our Susan from the museum, they started a project in 2009 looking at displacement sensors to look at components and response at the local level. Then one can, what I'm going to focus on further in this presentation is the overall, the global level, the overarching level including the complex objects with the structural functionality they will be subject to in an exhibition setting. Then you have, for our objects, they are load-bearing, so they have supports, and the ships have to function structurally. And that will give many effects that you can't predict on a component level. So in 2016, we set up a idea for methodology of monitoring, and we were looking at the idea was to monitor geometry, changing geometry of the object, and also the load distribution internally between our support system, to see if there were any changes during the seasonal changes in our age. So we did an evaluation of 3D monitoring. That is not trivial. There are many methods one can use. When it comes to climate, it is very important to have a short acquisition time frame, because you want to do your measurements in a short time to avoid changes related to climate during your acquisition. And to just put this into perspective, we are using structural light scanning to do 3D documentation of our collections, and to use this method to cover a ship like the Oseberg ship takes about 30 days. And that is much, much too long. The models becomes very nice visually, but it is useless when it comes to monitoring climate, because in a month's time we can have huge changes to the object during acquisition. So the acquisition time frame has to be short, and you need, the changes are not very big, so you want to be able to detect small changes, so accuracy and precision is also a primary factor. This brought us into photogrammetry with fixed targets. That means that we build up a system of targets that are permanently fixed to the object. On this picture, you see a small ceramic target on the upper board, and then on the board number 10. And then we have distributed this strategically according to the basic functionality of the structure, what we evaluate as important key elements to the structure. Then the position of these targets are measured every 4th week. And now we are down in approximately 6 hours to do one acquisition. So even though there is a window here of 6 hours, we have relatively small changes in climate during this time frame. So that was the geometry. The geometry, we use then fixed target photogrammetry. Then, in addition to that, we are monitoring load. Of course, it was very exciting to see how much load the different supports are actually exposed to, how it is distributed, and if this distribution is changing over time. So what we did was to lift the Oseberg ship on load cells all along the keel and all along the side supports. And we lifted the ship about 3 centimeters in 2018, and it's still there. and we are still logging the distribution of mass. So that is a continuous log going every day. The acquisitions for geometry we've done at a rate of 4 weeks between each acquisition. So how this actually looks when you combine the different data sets of shape, geometry, and load and climate. We are correlating then the load distribution and change in geometry with correlating that to the climate situation. So I would actually like to show you the software, how it is built up, how we built up the different components of the ship. It is a bit heavy and unstable to show in the presentation, so I've just put out one view and to show you how this can be applied. And what I want you to have a look at is the frame with the graph is the climate. The line in the middle is where we are at the acquisition, 24th of August 2018. Our age is 57.7 and temperature 21.4. There, the geometry, I put that to 0 at this situation, and we have lots of numbers here. The white numbers, they are numbers with load, and I just want you to pick out one, the front support, in this case, with a red circle. And then we can start running this and go 1 month, 4 weeks ahead. Then we see these vectors from the 10th board and all along the keel up in the stem is moving forward. And the whole ship, actually here, the whole ship is moving forward, and the load is fairly stable. I went back. Going further out in the autumn, October, our age 65, temperature 16.6. Then in November, it's slowly starting to decrease the RH, 61.3 here, 17.4 degrees. Heat has come on in the museum and it's getting drier. Now, related to the month before, we see it has pulled slightly backwards, and the load has gone down some kilos from 258 to 249. Then we move ahead to December. Now we see that ship has come back to our situation in August. And the load on the front support is now down in 209 kilos. Now the RH is down into on 47.2, temperature is 15 degrees. 15 degrees is sort of 14, 15 degrees is what we have inside the museum in the wintertime. Generally is November, December, January, February. Then we go into our driest season in January, February. Now we are at the red line. That's where we, that's the acquisition time and where we are at 47.2. Now we're going to move ahead. What is happening in between here? It's going a bit up and down, but we are more or less at the same level when we arrive in February, no, in January. And we see now the even though it's quite stable, we see the lag in the structure, and it's starting to really respond to the dry climate. Now the whole stem is pulling backwards related to the summer. It went forwards and it's gone through zero, and now it's back on its way inwards. And now we see the load that we started on, 260 kilo, is now down in 290 kilos. So quite a substantial difference on that support. Then we can move ahead. We see now we are now at the middle line of the graph, and now now we're going to move ahead to February. It's really now coming backwards several millimeters, 3.3, between 2 and 3.5 millimeters. The stem is moving backwards. Now we are at the maximum response of the dry climate in this stage project that I'm showing you now. And now we see the load is on 182 kilos. So we have moved from 260 to 182. In March, now it's getting a bit more humid, and it's pulling a bit forward again, and we can move even further to April. It was a bit up and down. It can't really decide whether it's going to go forwards or backwards, but the load is increasing slightly on the front support. At the end of April, we now see the trend of the graph. It's going steadily upwards, and the stem is pulling forward, and now we are up in 230 kilos on our front support again. In May, it has really turned, and it's getting more humid, and we are on our way back to our summer situation with around 250 kilos of load on the front support. Now the relative humidity is where it very often is in our museum in the summertime, around 70%. And we are seeing the increased response in our stem when we move on to June. And we are back on 260 kilos on our front support. And completing the cycle from August and then to 22nd of July, it's getting a bit drier, pulling a bit back, and around 249 kilos. So this was just to show you some of how one can use the combined methodology of looking at load distribution and change of shape, geometry of the ship. And we have many more components. It becomes very chaotic if I'm going to put all of them into one slide. So I've just taken out some of them. But here we can also see, I have put here a measurement at the support, and we can see how the structure is, if it goes up or down in between the support. Generally, it falls slightly more down between the support by mechanoabsorptive creep. It doesn't tend to go completely back. So we have a slight sort of, we have indication that there is a slight lack of regaining the original shape when it goes through many cycles of these movements. So this is another example of what we can do with these data to see. This is a strain plot. We put the same data from the fixed target photogrammetry into a plot for the whole Oseberg ship. And the deeper the color, the more strain and the more tension one can expect in these areas. And these plots correspond very much to the actual damages that we see on the ship. And we can also then further use the information that this gives us to tailor the allowable climate to avoid changes that are creating tensions, and to also be a very great help for how to understand our support system and how we can improve our support systems in areas of risk and for deformations. Another outcome of this is that we now, as you have heard, we are in the process of getting a new museum. So but with the engineers, they are making finite element models of these ships, and then we can feed these data also to the engineers. Then I see that I have used more than my time, and thank you.
So I am currently a PhD in Trondheim. I'm working in the MTP department, so the Mechanical Engineering Department here at NTNU. And as Susan has alluded to already, let's see if I can switch. Okay. I am looking at distempered paint, mainly looking at the physical and chemical components of distempered paint from Norwegian stave churches. To better inform or better understand the risks of damage for these historic materials. So what is typically done in our field? When developing a preservation plan or strategy, we're typically looking at failures resulting from chemical, biological, or mechanical behavior. During this presentation, I will only be talking about mechanical failures, or the way to monitor or look at them. Using one specific technique is actually called nanoindentation. But typically in our field, what we're doing is we're looking at macro size mockups. And from these macro size mockups, we are using techniques such as tensile testing or dynamic mechanical analysis to characterize these materials. As a result, we're carrying them out on mockups and not on historic materials themselves. But what if we could actually look at the mechanical properties of historic materials? Well, in 2011, and since then, several other research groups have done this too, but in 2011, Dr. Salvant, along with her colleagues at the Northwestern University in Chicago and the Art Institute of Chicago, performed mechanical characterization on samples taken from actual works of art. And then they looked at the mechanical properties that they recovered from the different layers. So you can see here, sorry, they indented on these different layers and were able to look at the hardness or modulus and distinguish between them. And they also compared them to mock-ups that they had made. Okay, so what is actually nanoindentation? Well, nano indentation, or the standard indent, consists of pressing a probe of a well-defined shape into a material and then determining a load displacement curve or load depth curve. So what you're doing actually is you take a stylus or an indenter with a well-known shape, such a pyramidal, you press it into your sample, and then from that you get a resulting load displacement curve, which you can see here. So you're either controlling the load or the depth, which is the displacement and in which you're indenting to. With this process, there's typically 3 stages, which are outlined here: the loading, the pause, and then the unloading. And from these different parts of the indentation scheme, you can get different material properties, which are listed here, such as fracture hardness, toughness, elastic modulus, and creep. So at the Getty Conservation Institute, there is a nano indenter lovingly called Annelies, which you see here. So on the left-hand side, this image here is the actual system itself, and in which it's positionally synchronized. So what that just means is you can see a little cross-sectional sample here. You would look at it underneath a microscope, select exactly where you would like to indent, then the system would send it over to this instrument here, which is the nano indenter, and it would carry out its indentation on that. Then it would send it back and you could actually image it. This entire apparatus is actually in an environmental chamber, which is pictured here, which allows one to control the relative humidity and temperature while collecting your data. And for those of you that are interested in which specific ranges this instrument is capable of, they're listed here. So Annelies is capable of looking at relative humidity and temperature within the schemes of 1 and 2. So for this presentation, I'm going to talk about 3 different studies and looking at 3 different types of materials. So first, we're going to start off with looking at the softening of ultramarine blue. Then we're going to look at testing of cross-sectional samples. And then we'll end with testing high pigmented paints, which is currently what we're doing. So the softening of ultramarine blue was carried out with 3 different groups, the Getty Conservation Institute, the Royal Danish Academy, and then also with Tveit. It was carried out as part of CMOP, the Cleaning of Modern Oil Paints Initiative, and is carried on since the ending of that. But I'm only going to talk about ultramarine blue, even though you can see here we have 3 different types of samples. So this is just a segment of that entire study that was carried out. And the reason why we're talking about ultramarine blue versus the yellow ochre or the cadmium yellow is because with the ultramarine blue, what we did is we looked at the effect of relative humidity. So if you recall with nano indentation, we're applying a load, which you see here in this didactic, and then we can measure the depth that is happening. Anytime you see something that is red, it's going to be the load. So here on the y-axis, we have the load. And then anytime you see a green, it's going to be the depth of that subsequent load. So you apply a load, and then you can measure from that the depth. So here on the X, we looked at 5 different relative humidities. So we looked at 35, at 50, at 60, at 70, and then at 83, all on the same material. So that means that we put the material into the tester. We equilibrated it at that relative humidity, and then we applied a load. So when applying a load here with this red at a relative humidity of 35, we needed to apply a load of 80 millinewtons to receive a depth of about 6 microns. For our testing for this specific sample, we noticed that a 6 microns showed relatively reproducible measurements. So the entire time we were changing the load, which is this red curve, to always reach about 6 microns depth. So that means that as the relative humidity increased, as we're going to the right, we actually needed to decrease our load, so what we're applying, to keep the depth at the same 6 microns. So we have the RH and the applied load are inversely proportional for this specific sample. What we then did next as part of this study is we actually plotted the softening of our paint by water absorption. So this is a part of a study where we were also using dynamic vapor absorption. And you can see here that the RH increases, as the RH increases, the depth to keep it at 6 microns, the load is decreasing. And we can see, yeah, and I already stated that it's inversely proportional. Okay, so we're looking at the softening of our material based off of water absorption. What we can do with nano indentation is something that is all post-processing. So with indenting, you apply a load and then you look at the depth. But from the load displacements curves, we can also look at different material properties, such as something called the reduced storage modulus, which pretty much just tells you about the stiffness of your material. So the higher the reduced storage modulus, the stiffer it is. The lower the reduced storage modulus, the less stiff it is. So as you apply a higher relative humidity for this ultramarine blue, you can see that the stiffness modulus is actually, or the stiffness, the reduced modulus is actually decreasing. So it's becoming more fluid-like. For this, you can also see this in the pictures to the right. So if you remember in the slide before, at the higher RHs, we actually needed to reduce the load. But to make a didactic or to show an example of what's actually happening, we applied all the same loads at 50, 60, and 70. So we used a max load of 30 millinewtons just to show you how less stiff the material is becoming as the relative humidity is increasing. So all of these, because it's a pyramidal shaped indenter, is what is resultant from the indent at that specific humidity. So as the humidity increases, actually the area of the entire indent is increasing too, because it's becoming less stiff, so less resistant to the applied load. Another property we can look at is viscosity. So as the relative humidity for this sample keeps getting higher and higher and higher, the material is becoming more viscous. And this is also shown through these pictures here on the right. So at the lower relative humidity, it's a bit more stiff, it's less viscous, so it's actually keeping the shape of the indenter. Whereas you increase the relative humidity, you get something globular, like at 83%. And that's because what's happening is the material itself is actually sticking to the indenter because it's so fluid. So with this specific part of the study, we were able to measure the properties of the paint films. I don't know if I mentioned that, but these were all paint films and not actual cross-sectional samples as a function of relative humidity, and trace the alterations in the mechanical properties of oil paints resulting from the water absorption. So how much water is being uptaked by that specific material. The next study I will talk about is cross-sectional samples. So as I alluded to before with Solvant's study, they were actually looking at cross-sectional samples. So what we tried to do next is we tried to look at the probabilistic distribution. So how probable the different mechanical properties are distributed throughout a specific cross-sectional sample. But instead of looking at historic material, what we decided to do is we decided to start with titanium white acrylic-based paint from Golden Artist Colors. And the reason why we chose this specific material is because Eric Hagen at CCI actually has done quite a bit of analysis on this specific material using macro size samples. So that's just shown here as an example. You can have UTM samples or DMA samples, then relative to the historic material sample, although this is a very large cross-sectional sample. So what we were trying to do is we were actually trying to look at the effects of embedding this material with a specific resin. So what we chose is we chose Technovit, and the reason why we chose Technovit is because it's a fast curing resin. So unlike some of the epoxies, Technovit can more or less be ready to finish curing in 45 minutes. So then that allowed us to make several different samples. To actually look at this embedding process, what we needed to do is we needed to look at 3 different materials. So we needed to look at the free film itself before it was embedded, and then we needed to look at the surrounding resin, so the Technovit, And then we need to look at the sample itself, so the embedded paint sample. When developing our protocol, we actually developed our protocol based off of the free film because it had infinite space because it's nano indentating. So that means the indents are really quite small. And if these are large on the scale of nano indentation, it's infinite amount of times we can test that specific sample. So what does it actually look like when we're indenting across a cross-sectional sample? Well, we performed something called a matrix, and in which we indented throughout the sample. So we indented in the resin and then into the paint film itself and then back into the resin. And this is actually just an example of what we did because we indented on 2 different samples and resulted with a matrix of about 105 indents total for both samples. So for these 2 samples, you can see them pictured here on the right-hand side. Once again, what we were looking at is we were looking at the reduced storage modulus. So we're looking at the stiffness. So these are the 2 samples. We looked at a sample that we called large and a sample that we called small. And so we then indented through the sample. The small sample, we were able to indent the entire sample itself, where with the larger sample, we just indented through the middle section, which you can see here in this color contour plots. And what the color contour plots are actually showing you is the reduced modulus. So at a higher reduced modulus, you're actually going to have a red color, and at a lower reduced modulus, you're going to have the blue colors. And so that just means that with a blue color, there's actually less stiff material. With the red color, there's going to be a higher stiff material. Which is understandable because we're embedding it in an acrylic-based resin, even though also titanium white is also an acrylic, but these Technovit is quite stiff. So that's why you can see this area here is a bit more yellow and green, where in the middle, it's blue. Also, if you recall, we based our entire process off of indenting making our indentation protocol based off of our free film. So it makes quite a bit of sense that here in the middle, if I could show you other data, we actually received statistically significant information. So that just means that the amount of air within the middle of our sample was actually quite low. And what the biggest difference between these 2 samples is telling us is that actually with the smaller sample, there's quite a bit of infiltration of the acrylic polymer from the resin feeding into our material, which was obviously a complication if we're trying to measure the modulus or any type of response of the material itself, but we're actually measuring a mixed composite of both the resin and the historic material, even though this is not historic currently. How do we actually go about that? Well, in the later works for this group, that was actually addressed on how to look at the proximity of the paint resin interface and how to develop a testing protocol along with a mounting protocol that reduces the amount of infiltration of the embedding resin into the test material. So then the last study that I'm going to talk about is actually what we're doing right now, is looking at distempered wall paintings. So since 2018, we actually sampled from a couple of the stave churches here in Norway. And with these samples, they're distempered. So they're highly pigmented, granular, and quite porous. So if you recall all the other samples we've looked at, the first one was an oil-based paint, the second one was an acrylic-based paint, and this is going to be an animal-based paint, but the type of distribution of the pigments themselves are actually going to cause a bit of complications. So with nano indentation, what's happening here is actually the value of the reduced storage modulus is strongly being affected by the surface roughness of the material. So here what we did is we mounted our sample because we knew since they were going to be quite porous, using a liquid resin would cause further issues. So we mounted it and we tried to indent from the top down versus as a cross-sectional sample. But by doing that, we received quite a bit of spread of information. So here in this plot, you have counts. So counts just means how many times that specific measurement. So here we're looking at the reduced storage modulus occurs. So by then indenting on top of this sample, we received different responses. And the reason why we're receiving different responses is because it's made out of different pigments, but also because of the surface roughness. So then what we did next is we actually looked at a CT scan of these materials. And what it's showing is that depending on which area you're indenting on, it will obviously have a different response. So if we're indenting on something that is has a void below it, it will respond differently than if you're indenting on top of something that is quite compact or something that is loosely compact. So with all of those things, I just really want to stress that nano indentation is actually a really interesting technique that allows you to look at localized properties. You can also use nano indentation if it's inside an environmental chamber like the one at the Getty Conservation Institute to look at the effects of temperature and relative humidity, along with, we showed in other studies, you can look at treatments. So we have also looked at what happens when you do different types of surface treatments, such as swab cleaning or a treatment that's not necessarily a treatment, but it shows the full-on effect of what could possibly happen if you leach all materials by soaking your paint film in some type of solvent for 24 hours. So 24-hour immersion. And however, when developing a indentation scheme, you really need to take a couple of things into consideration when it comes to historic materials or artist materials. You need to really think about how you're preparing your sample because a lot of our samples are quite porous and small, that they need to stay situated in an area without being fully infiltrated. Otherwise, you're going to look at a composite material, which can still be beneficial, but you need to understand that that's what you're looking at. And then on top of all of that, any type of restrictions for this type of testing isn't a restriction or limitation of the instrument itself. The instrument is looking at localized testing, but really what's happening is we have such small material, which I don't need to stress to you guys at all. But with that comes the complications such as chemical analysis of what are we actually looking at and how are we actually doing that. So last but not least, there are several people I would like to thank, mainly my supervisors, Chiara Bertolini, who is my supervisor here at NTNU, my co-supervisor, Michaeł Łukomski, the science department at the GCI, along with all the previous and current members of the Managing Collection Environment Initiative, and the partners of the Symbol Project. Thank you.
So, as it was already introduced, we are going to talk together. There will be two separate talks. We will switch between us after first 15 minutes. We'll talk about the recent update of the ASHRAE chapter, as well as some specific tools which we are developing to support the analysis of the temperature and humidity conditions in the museum. And let me start this talk with acknowledging something which was probably acknowledged already many times during this conference, the fact that defining the proper climate conditions for the museum is a really complicated task. And this is a complicated task because a museum have got those conflicting needs and conflicting directions of operation. So on the one side, in the museum conditions, we would like to preserve the objects in the best possible way, but at the same time, we would like to provide the access to the collection and do all these things within some limited resources of the museum. And the resources are always limited, doesn't matter how rich the museum is. So within the Managing Collection Environment Initiative, which is one of the programs of the Getty Conservation Institute, we are trying to develop and provide evidence-based processes and tools to empower those who make decisions about the climate conditions in the museum. And those are typically very practical tools, and one of those tools are the guidelines available from the field. And we had this opportunity to work with the international team of experts on the recent revision of the ASHRAE chapter. This is a chapter of the handbook of the American Society of Heating, Refrigerating and Air Conditioning Engineers, and the chapter on the museum, galleries, archives and libraries was first published in 1999, and later during many years it was constantly updated. It was great that we were able to work on this revision and improvement of the chapter, because in fact this chapter is the most popular chapter from all in the ASHRAE guidelines. And I believe this is because this chapter is extremely practical and therefore very appealing to the conservation and museum field in general. So this pragmatic approach is based on the risk management principles. It refers to existing research on the environmental response of the hygroscopic objects constituting collections, and what is, I think, the most important is that it shares the museum experience, especially this experience that many collections are very well maintained and preserved even in not ideal climatic conditions. So ASHRAE chapter is a provides a very precise information about process. So starting with planning, going through the design and implementation of the climate control strategies, it is focused on the engineering community. So it provides engineers with insight into complexities of environmental management in heritage sites. And I think this is very beneficial, because it really names the problems of the climate control strategy in the engineering name, giving this tangible and very concrete nomenclature. So chapter works as a tool which can improve communication among stakeholders, those who are involved in defining climate control strategy in the museum. During this 2019 revision, we were focused on the decision-making process for planning, designing, and implementing strategies for long-term preservation of the cultural heritage, which means that basically we were trying to increase the sustainability of the museums. And we did it through exploring possibilities to reduce energy consumption in the museum, and by introducing more flexibility in control. So basically giving people more options and discussing what are the consequences for those options when we develop particular climate control schemes. And also we found that it is extremely important to focus and stress on more integration between departments when developing the proper strategies for the museum institutions. We also took care of merging information in the chapter with the other available guidelines in the field. So I just listed some of them, and all of them were created after 1999, which is after when the ASHRAE chapter was first created. So it was very important for us to provide the information which is compatible with all knowledge existing in the field. The first element of the chapter, the first section, which we added in this revision, is the decision diagram for environmental strategy and development. And I think this is really important improvement of the chapter. In this section, we are trying to define the decision-making process, starting from the context in which we are making decision, going through the pre-design phase and the design and implementation. So really the starting of the discussion is about the mission and strategy of the institution, what actually we would like to achieve, who is our audience, what is expected from us, and then looking through all the complications and limitations of the site and collection, we can go to the design and implementation phase. And the element which I personally believe is always very complex in the defining the climate control strategy, and something which is often the source of a failure in the success of this implementation, is that the process is comprising so many different people and parties. And this is very important to understand who in each step should lead the discussion, who should be consulted, and who should be informed. And in this scheme, we try to name all those parties to make the decision very collative, like everybody who should be informed and have a say in the process can have a chance to do that. So whenever we are in this process, whichever place in this scheme we are, we can always find the next logical step. So even if we finally evaluate and revise our system and our strategy, we always need to look how it performs and how we can improve that in the future. So this is always a process. And this process is working really in combination of three elements. Defining the appropriate interior conditions for the collection really depends on the performance of the building, something I will call building envelope, and external climate for our museum. And those three elements are inherently interconnected in the ASHRAE chapter. And we can start to discuss the problem of appropriate conditions from any of those. And I will start from exterior climate, because in this new chapter, this new version of chapter, we added the methodology for defining climate zones following the American National Standard Institute, and this information is now in explicit way provided in the chapter. So now everybody can find directly information about in which climate zone our museum is located. And this information can be directly used for defining what is possible and what is not possible for our museum. And this information is directly used in this table 12. This is just part of the table 12, just example of how we combine type of control, climate zone, and envelope performance on the building. So in this example, what you can see is that the type of climate control B, which means some particular limits of temperature and humidity for the collections, can be obtained by building with the different envelope, which means different isolation, air exchange rate, and control of the moisture flow in different climates. So we can see that if we are in a particular climates, our building needs to be different to obtain particular level of control. And you may think that this table is a little obscure with those strange terms. However, I would like to assure you that in the chapter, all those elements of the tables are very precisely explained, and they are very clear for engineers working with the buildings. And finally, there is a table 13, which defines those temperature and the relative humidity specification for collections in different buildings. And this is this core of the ASHRAE chapter, probably the table which is the most famous in the chapter. And this is again only just part of that, showing the climate control category B and C, but the categories are starting from AA and going to D. And when we look at the climate control type, we've got the definition of the climatic conditions, and this is defined by the long-term outer limits, annual average, seasonal adjustment, and the short-term fluctuations. And for each category, we've got explicit information about benefits and risk for the collections made of different objects. So all in all, we've got 5 elements which are interconnected, and when we read the ASHRAE chapter 24, it is leading us through the decisions and information about access to collection, type of internal control, which is linked with the risk for the collection, but also type of the museum building and climate zone. All those 5 elements, as I said, interconnected, helps us to understand what is needed for our institution, what is possible, and also what is sustainable. Additional change which we introduced was decoupling the loan exhibition from this general scheme. We decide that we should not define for the loan exhibition the risk for collection and strategy for organizing exhibition in the same way as other part of museum. And in explicit way, we said that the climate for the exhibition should be based on objects' historic climate, risk at borrower institutions, and also risk related with the transport of the objects. One should also remember that chapter 24 of ASHRAE handbook is still focused on engineers, and you can find a lot of information inside about design, control, and management on the indoor environment, which is linked with the most advanced and up-to-date engineering technology, and of course the conservation science. So this is still a very practical document for the engineers. So summarizing this first part of the talk, before I hand it to Vincent, I would like to say maybe two things. One is that in this recent revision of the ASHRAE chapter, we introduced a lot of new elements and information that can improve communication between the conservation and professionals in facilities and engineers. And this was done by adding a lot of contextual information. The length of a chapter after revision is more or less 2 times longer than it was before, and it is because we decide to very methodically describe the consequences of making particular decision or not making those decisions, or providing some alternatives to just increase the possible flexibility of the decision which can be made. And the guidelines in general promotes this flexibility very much. So the institution can very strategically allocate resources to make decisions in context of their structural, geographical, and organizational limits. And it always says that there is no one size fits all. We need to look for those flexible solutions to develop strategies which fits the best our institutions. And to do that, and do that well, we really need to understand conditions in our museum, and therefore we, on the one side, work on those guidelines, but the other side, we also work on developing tools and methods which can help analyze situations in the museum and provide the easy way to compare museum conditions with the guidelines and give us tools to help make those decisions. And now I would like to stop sharing my screen, and I will hand it to Vincent, who will present the second part of this talk.
All right, thank you, Michaeł. So I'm going to build upon Michael's presentation. I'm going to talk about the expanded analysis of temperature and relative humidity data. And this part of the presentation is co-authored by myself and my colleague, Annelies Cosaert. Temperature and RH obviously is commonly collected in the cultural heritage field. And you really have to understand this data set to effectively apply Table 13A in the ASHRAE chapter. So going back to the table, here's now the full table. And we can see all the 5 control classes, or I'm sorry, 6 control classes. And I'm going to summarize this in the following slide. Classes AA, A1, and A2 are the tightest control classes. And they're really intended for implementation in a modern purpose-built structure. Classes B and C extend that range and are implemented in structures where you need to reduce stress. So for instance, a historic house museum. And then class D is really intended for open structured buildings, and you're trying to limit high relative humidity conditions. A key point about the revision of this specific table is that we specifically chose to move away from prescriptive set points, 20 degrees C, 50% RH. And we instead wanted to center the set points around the historic annual average temperature and RH of the permanent collection. And this is a reflection of the environmental history of the objects, as well as the fact that these collections reside in very different climate zones around the world. And trying to use a prescriptive value can be problematic in that context. So going back to this slide, the MC initiative has explored the topic of TNRH analysis and visualization. And our earliest foray was my development of something called the GCI Excel tools. And this was a tool that gave us options for analysis and visualization. It was first presented for the MCE course that was discussed earlier. And we recently introduced it at a couple AIC workshops this past summer. Excel was chosen because it was a common platform that was easily accessible. The functions in the tool are extremely transparent, so it makes it a really great teaching tool. But even after the course, it's actually proved to be a practical use by the course participants as a way of analyzing our data. The advanced analysis of temperature and RH has multiple benefits. The first is acquiring a deeper understanding of the museum environment. And this is achieved by using different analyses and visualizations that have complementary objectives, giving you a more holistic view of the environment. It also improves communication with the stakeholders involved in environmental management. And here you can use these different visualization options to support the narrative purpose, and then to also match to the expertise of the viewer. And in a number of cases, trying to match the expertise of the technical staff with more technically minded visualizations has kind of given them credibility and allowed them to participate more fully in the discussion with HVAC engineers and facilities. It also supports the decision-making for sustainable and environmental management. And you're able to identify collection risks and guide the use of either non-mechanical or mechanical environmental strategies. So what is advanced temperature and RH analysis? In the next few slides, I'll go through a sequence of plots to try to illustrate this point. Here, we're looking at a common time series plot of relative humidity. RH is shown on the y-axis, and time is shown on the x-axis. And here's the RH data that you would pull out of your data logger. But from this, you can calculate other things. So on the bottom of the orange line, I'm calculating the 24-hour range. So here I'm looking at a 24-hour window and determining the fluctuations, and then sliding that window across that data set to create another calculated parameter. In addition, the line in red is a 7-day moving average. Here I'm looking at a 1-week window, calculating the average, and then sliding that across that data set. The 24-hour range acts to give you a sense of the short-term variation. The 7-day average serves to reduce the influence of the high and low values and could be more relevant for objects that respond more slowly to RH change. In addition, you can overlay on top of these plots target zones. These are the conditions that you're trying to achieve in your situation. The target at the top is set from 40 to 60% RH, so basically BESO RH conditions. And you can see when the values are in and out of spec. And at the bottom, I have a target from 0 to 10%. This coincides with the short-term fluctuations that are suggested by class A2 and class B from the ASHRAE chapter. We can also look at our information outside of the time domain. And here I'm looking at probability. We're looking at cumulative relative frequency on the y-axis and air temperature on the x-axis. And I have these two lines that are corresponding to exterior data and interior data. I've also, again, overlaid a target zone from 20 to 25C. And an easy way you can use this plot is you can identify these intersections of the interior line with the boundaries of the target zone. So here I've done that, and I can see that this intersection with a 20 degree C for the interior data corresponds with the 48th percentile. And this means that 48% of your data set is under 20 degrees C. If I take a look at that other intersection with 25 degrees C, that coincides with the 91st percentile. So this allows me to say that the canal room temperature is inside this target zone during 43% of the period. This plot really gives you a granular look at the probabilities in your data set. I can also look at probabilities in an entirely different way. So here we're looking at a box plot, the same data, but organized in another manner. So on the y-axis, we have air temperature. On the x-axis are the locations. So canal room on the left and exterior on the right. And the probabilities here are shown by the position of the whiskers and the box on the plot. This box, as you can see in this legend, corresponds to the middle 50% of your data set, which is also known as the interquartile range. But in practice, what I'm looking at is how narrow or wide this box is, and how do these boxes compare to each other. So I can see that the canal room has a tighter range than that of the exterior, and it's situated at a higher temperature than that of the exterior. Now, this is a very simple example, but the box plot really shines if you're looking at a lot of spaces. So here we're looking at about 20 different spaces, and the thing you want to focus on are the position of those boxes. And I'll highlight two boxes that are very different than all the other spaces. Similarly to the previous plot, they have a tighter range of temperature, and they're situated at a higher value. And these indicate two spaces that are climate controlled. I want to end with a discussion of the psychrometric chart. And the beauty of the psychrometric chart is it allows you to look at these variables in concert. So temperature and RH are things you collect, but they're not the only way to thermodynamically describe a parcel of air. There are a number of other variables that can be calculated from just T and RH. The psychrometric chart is situated with a temperature on the x-axis, humidity ratio on the y-axis, and that is a sense of how much moisture is in the air. And relative humidity is defined by these curved lines of constant RH. They're also called isohumes. So you can plot your data on this chart. And in green, I'm looking at the exterior data. And in orange, I see the interior data. You can see that the exterior data has quite a broad spread in terms of both temperature and RH. And the interior data encompasses a much tighter space. I'm going to focus now on the interior data. And you can break that up in different ways. Here I'm choosing it to do it by season. So blue is winter data, red is summer data. Then you can also overlay a target zone. And unlike the previous charts, the target zone here is a function of both temperature and RH. So it's situated between 15 and 25 C on the left and right, and between 40 and 60% RH on the top and bottom. And you can see it's curved because it has to follow these curved isohume lines. Another beauty of the psychrometric chart is that the direction of movement coincides with a psychrometric strategy. So if you're moving up on this plot, you're humidifying. If you move down, you're dehumidifying. If you go to the right, you're heating. And if you go to the left, you're cooling. So if you focus on a point that's outside of the target zone, say here to the right of the target zone, if I need to get that point into my target zone, I can take a look at this psychrometric chart legend and see the type of strategy I need to employ. So if I need to push it to the left, I would need to employ a cooling strategy. So it extends your kind of understanding of the data beyond just stats, beyond just numerical characterization, but also tying it to the actions that you might need to take in order to modify your environment. Going back to the ASHRAE chapter, the psychrometric chart can also be used to depict the different control classes. Here I have a situation in which I have an annual average of 42% RH and a temperature of 21 degrees C. And here I'm showing AA control. And obviously it's quite complicated, but I'm just going to go through a few different ones. Here's AA, here's class B, and then here's class D control. So it allows you to talk about these control classes, not looking at temperature and RH individually, but together. How do we do all this? What's the toolbox that we have to do temperature and RH analysis? Here's a list of a number of tools that are available that can give you insight into your data. And they all overlap in different ways, but the thing I'm going to focus on is in how they differ, because oftentimes there's a specific motivation by the institution to create these tools. And I'll talk about a few of them. In terms of the GCI Excel tools, it's really trying to promote flexibility in how you show your data. eClimate Notebook from the Image Permanent Institute also shows your data, but it has a strength in collection risk indices. So time to mold, chemical risk factors. If we look at Harry E. from the Jersey Haber Institute, it's focusing on the mechanical risk in terms of stress and strain. And it's done in a way that's very object specific. And then at the end, if we look at Climate Consultant from UCLA, it's coming out of the field of building physics. And it's taking a look at exterior weather data and then suggesting different design strategies that you can employ for your interior space. Now, there's a lot of other tools in development as well. I'm going to focus on the Victoria and Albert Museum. A colleague there named Braovac has been developing a number of environmental analysis tools using R. And R is an open source programming code, which is kind of the wave of the future. Braovac and Melissa King at the Smithsonian recently started something called Concode Slack. Concode is coding for conservation, and it really defines the intersection between data analysis or data science and heritage conservation. And here is a number of colleagues that are trying to talk about how we can use different kinds of code, R or Python, to really improve environmental analysis practice. It just started a month ago. It's only been talked about through word of mouth, but there's already been 62 people joining in from all over the world. And in fact, we've started to look at how we can adapt our GCI Excel tools using R. The MC initiative has disseminated information on this topic in a few different ways. This past summer, Annelies, Jeremy Linden, and myself offered a few workshops to talk through these different tools, explain how they work, give them a practice in analyzing their own data using these tools, and then presenting different case studies to show how we can use these tools to kind of understand our situations. We're currently trying to develop an asynchronous version to make this information more widely available. In this coming year, there's a few publications that we have. There's an ICOM-CC article by Annelies and myself that takes a look at a survey of these different tools and describes interviews from different practitioners in terms of how they're using tools to analyze their data. And we also have a report that summarizes a meeting we held at the end of 2019 that brought together a multidisciplinary group of tool users and tool developers to describe the state of the field and how we can move things forward. Transitioning now to our future work, the first thing is trying to revisit the ASHRAE chapter. So as Michaeł stated, it was a chapter that was done in 1999. It stayed relatively static for about 20 years and then had a huge revision in 2019. It has another provision planned for 2023, but I think it's important for us to critically assess how effective and how practical this chapter is for the cultural heritage field. And This will inform the next iteration of the chapter. It's also of interest to us to look at the response of museum objects in galleries as institutions look to widen the environmental parameters. And our main tool for doing this is using acoustic emission. And as I've discussed, we're interested in supporting the use and development of different types of tools, temperature and RH, but also data sets outside of that, looking at pests, looking at light. And then, you know, being in the pandemic, we've obviously seen a lot of different presentations of information on the web and through these Zoom calls. And it's of interest to us to broaden the accessibility of our educational materials to the field. So as always, it takes a team to really achieve these types of tasks. Here's a list of everyone that's been a part of the MCE team since its inception. The names italicized are the current members, but everyone on this team is always a part of the MCE initiative. And I just want to acknowledge all their efforts in supporting the work. So I'd like to thank you for your time and your attention. Thank you.